So we know that quantum numbers define our atomic orbitals. So let's take a little bit of a closer look at what our atomic orbitals look like. So when we go to visualize an orbital, remember that they have characteristic shapes, and those shapes are defined by their L value. In addition, your principal quantum number changes what the cross section looks like. So if you look at this image here, you'll see that an N of 1 has a single sphere. N of 2 has two concentric spheres. So we have a small sphere inside of a larger sphere. And then N of 3, we have now three concentric spheres, small, medium, and then large. And one thing I want to point out here is that the blue represents electron density and white is a node. A white is an area of node density. So if we look at an s orbitals are always spherical in shape. And if you look at the 1s orbital, which is shown on the far left, you see that we have a single blue sphere, blue being actual electron density, white then being node, where there's no electrons. Well, actually, in this case, there is no node. The white at the edge is just where our orbital ends, and then there's nothing outside of that. But if you look at N of 2, the middle of the image, you'll see that there is white space between two sections of blue. That white space separating two areas of electron density is a node. And for N of 3, we have two nodes. So 2s tells us our principal quantum number is 2. S tells us the shape, which then is correlated to an L. So when L is equal to 0, we get our S shape. We know it's equal to 0 because S exists at N of 1. Our 1s is the only orbital in the principal quantum number 1, and L is only allowed to be 0 when N equals 1. Our p orbitals, now these get a little more interesting. Again, these are kind of dumbbell or peanut in shape. And so you see on the far left sort of cloud image, and that's a little bit more accurate of what you would visualize the electron doing, or the area where the electron is likely to go. But then on the right, you see three sort of cartoon figures. These are drawn. They're a little easier to draw and see what's going on. And so there are three p orbitals, and each p orbital is aligned along one of the axes. So we have one along x, one along y, and one along z. And these three orientations correspond to our m sub L value. So remember, P first appears at n equals 2. When n equals 2, the maximum L can equal is 1, and for a value of L equals 1, m sub L can be -1, 0, or +1. So that's three possible orientations, and we see those three orientations here with our p orbitals. You will want to know what these p orbitals look like and be able to identify them just by looking at them. Similarly, the d orbitals mostly look like four-leaf clovers with one oddball out, and that's the second one in from the left. You can see that one kind of looks like a p orbital with either a hula hoop or a donut around it. And that is the exception. The other ones all look very, very similar, but they are all d orbitals. And these have 5 orientations corresponding to an n of 3, where L is 2, and m sub L is -2, -1, 0, +1, and +2, giving us our 5 orientations. You will also want to be able to identify d orbitals just by seeing them. Now in hydrogen, we have a special case because hydrogen is the only element with a single electron. And when we have one electron, it turns out that the energy that electron is at is dependent only on the principal quantum number. So you see below an energy diagram, n is 1, the electron I should say, because we have 1, the electron is at 1 energy. N of 2, 1 energy. 3, 4, so on and so forth. And it doesn't matter which subshell it's in or which orbital it's in. This is not true for multi-electron systems. So for every other element other than hydrogen, when you have more than one electron, those electrons can repel from each other. And that causes our subshells to do something called splitting, where our s orbitals tend to go lower in energy, p orbitals are higher, d higher, so on and so forth.